And my name is Kosh Nasri. I'm a 10th grader from Orlando, Florida, in the United States. So, some background about me is I've been conducting honeybee conservation research for about 4 years now. And what I focus on is treating for a pest of the honeybee called the varroa mite, and it's a parasite that feeds on the fat bodies of bees. So, I used an organic treatment to treat for these varroa mites for the past 4 years.
So my name is Atreya. I'm a student at Yale, and I'm a honeybee researcher. I've been doing honeybee research work for the past 6 years now, and I also do One Health research. So we're here today, and our session's titled "Pollinators, Climate, and Public Health," and we're focusing on bee-centered solutions for food security. So COP30 here in Brazil has been framed by the government and both the organizers and stakeholders as the COP of implementation. And it's the first global stocktake into real action. And we sit here in the Amazon, and we can feel the humidity around us and really the impacts of these different climate change issues. So our session will be focusing on three major pillars, which all compose One Health, and these are agriculture and food systems, forests, oceans, and biodiversity, and then human and social development.
So, looking specifically at pollinators, honeybees are responsible for 80% of global food and crop pollination. One in every 3 bites of food we eat every single day, and $183 billion to the global economy annually.
So pollinators are extremely important, including things like bees and butterflies and also bats. And when pollinators decline, people don't only eat less calories and less food, but the quality of the food goes down because bees perform pollination of things such as different berries, almonds, and these are all very rich in terms of their nutrition. And so COP30 has been recognizing this with discussion on food systems and nutrition, which is being increasingly recognized. And for rural communities, especially here in the tropics, such as the Amazon adjacent regions, pollinator decline is threatening not only income but also cultural traditions. A lot of these farmers have been doing these things for generations, and this is really impacting their livelihood and also their well being. And pollinators aren't just a biodiversity issue, they're also a food systems and a public health issue, which is what these COP30 agriculture and health pavilions are really targeting.
So here in Belém and the global south especially, we're living through climate extremes that are affecting our everyday life, and it's something that the COP30 negotiators are talking about every single day. So some of these things are stronger storms, droughts, floods, and heat waves. So how this affects bees is the heat waves push the hive temperatures beyond what the brood can handle. The droughts and rainfall wipe out the flowering plants that the bees pollinate, and it also causes shifts in the bloom timing. So the flowers peak before the bees are ready to pollinate these different plants. And these are already huge causes and devastations to honeybees, but when this is paired with existing stressors like varroa mites, pesticides, and habitat loss, the result is unstable colonies and eventual colony collapse disorder. So when COP30 talks about a massive funding gap, hundreds of billions of dollars are needed by 2035, and it's not just that COP needs to focus on, but rather helping farmers and beekeepers help out their pollinators.
And one of the biggest signals that we're seeing here, something that I'm especially happy about, is the youth representation that's being conducted, especially if you go around at all these pavilions. They're much more involved in the process, including negotiations. And today we'll spotlight two complementary youth research projects, the first of which is a cost-sharing and eco-friendly carbon dioxide-based approach to controlling varroa mites. And this is developed with USDA, the University of Florida, and 3M Technologies. And then I'll be sharing how we can use bees as climate sentinels through pest management work that I've done over the past 6 years, and really looking at how we can turn this bee data into early monitoring systems for food and health at the community level. And after this, we will have a mini implementation lab after the lightning talks, where we'll use this pavilion to really ask four key segments. The first of which is what climate smart apiary management looks like for small placeholders in the Amazon, Africa, and Asia regions, and then looking at regulatory and safety steps needed before integrating these pest management practices for pests such as the Varroa, which we will be talking about, and then how IoT, AI, and community service can be implemented in low resource settings. And then finally, we'll be looking at finance and policy incentives for this crop.
So I'll be looking at the Varroa mite, the biology of it, and some control. So some background about the Varroa mite is that the Varroa mite originated from the Asian honeybee and it shifted to the European honeybee. And in this map right here, you can see countries that have the Varroa mite, and almost the entire globe is in red. So this is a massive issue. So the Varroa mite, the adult females are reddish brown and they're around 1 millimeter in length. So they're very small, but have a huge impact inside of the honeybee hives. So they attach to the bee's body, they deplete the vital resources and body fats. So how this impacts the bees is that it impairs their immunity by feeding on the fat body stores, and this leads to impaired immunity, reduced longevity, wing deformities, and increased susceptibility to other types of pests. So varroa mite infestations can cause up to a 45 to 60% annual bee decline every single year. And this isn't a massive amount, especially considering how useful and contribution that the honeybees give to the global economy. So these are some of the pesticide treatments that are currently used to treat for these varroa mites. And while they are effective, they have severe environmental contamination risks and are extremely harmful in the long run while being incredibly expensive. So also, varroa mites develop resistance to these pesticide treatments, and this leads to the pesticide treatments not being a sustainable solution over the long run. And also, the two leading pesticide treatments that are used for these varroa mites are called Apivar and Comifos, and they're actually classified as hazardous by the EPA and lead to contamination in hive products like honey and beeswax. So I decided to select CO2 as a substitution to these toxic pesticides, and I selected CO2 for an effect it has on insects known as hypercapnia, which is the acidification of insects' blood. So this I applied in the laboratory setting, and I found that varroa mites could theoretically be used and treated by a CO2 spray. So I tested this in the lab where I exposed bees and varroa mites to 10 varying dosages of carbon dioxide, and I found that the most effective dosage was a 30% solution. Next slide. I found that the most effective solution was a 30% solution because it was very effective in the varroa mite mortality and very effective in the honeybee survival. So I ran some statistical analysis, which also showed the exact same result, that the 30% solution could be a very effective treatment in the long run. And this is further statistical analysis, which revealed the same result. So in the next step, I ran a long-term trial where I looked at the long-term effects that the CO2 had, and I found that the CO2 treatment had no effects on the bee's lifespan. So this shows you right here, the 30% solution in red had no long-term effects on the lifespan. So this year what I did is I created a prototype that the beekeepers can use in their everyday practices to treat for these varroa mites. So what I developed is something that I like to call the mite blower. Next one. So how this works is that it releases CO2 inside of the hive, and it has these 9 tubes right here that are designed to lay on top of each of the 8 frames in a commercial beehive. So the CO2 is dispersed through this tubing and sinks to the bottom of the hive. And I found that the CO2 was equally as effective as the leading pesticides while being significantly cheaper and also not having any of the contamination risks that the pesticide treatments have. And this shows that result, that the CO2 was slightly more effective than these pesticides. And this is also some statistical analysis that shows the same result. So next, I created an artificial intelligence model that the beekeepers can use to predict their future varroa mite levels inside of their hives, which is unlike anything that has been done in the industry. So the model is around 98% accurate, and I'm currently working on making this an app that the beekeepers can use in their everyday practices. So I also created two more prototypes. The first one is a sticky trap that the beekeepers can use with this app that I am developing to predict their future mite levels, and also a CO2 absorption trap to mitigate the CO2 released from this hive treatment so the system is eco-friendly. And overall, the data indicates that this mite blower treatment that I developed could be used as a long-term solution because it is around 1/10 of a penny per hive treatment versus the pesticides, which are nearly 13,000 times more expensive. And I'm extremely happy with this project and the results, and I'm working on filing a patent and publishing these findings in a peer-reviewed journal.
Yeah, so I can take it from here and begin my lightning talk. So my research is a fifth-year project which focuses on capturing the small hive beetle, which is an invasive pest species of the honeybee. So as we discussed, honeybees are extremely important, performing 80% of global food and crop pollination. However, statistics show that these U.S. hives have been declining at a 50% rate annually, and beekeepers are seeing losses anywhere from 60 to 90% every single winter, and this is extremely alarming. So the pest that I was focusing on is the small hive beetle, and this is an invasive pest species of honeybees. And it essentially goes into the beehives where the bees exist, and then it defecates everywhere and consumes the bees' honey, the pollen stores, the cappings, the comb, and also the bee eggs. And that's how it causes damage in the hive. So in the first year of my research, I was looking at testing 7 organic small hive beetle attractants. And you can see on the bottom right is a picture of the trap that I was using. So this plastic trap was filled with these organic agents, and these things ranged from scented oils to yeasts to fruit purees and even beer. So alcohol was also used, and amongst all these compounds, the beer was found to be the most effective by far. And this was very surprising as it was mimicking the pheromone interaction with the beetle. And the fermentation that occurs in the beer is likely what was making it so effective. So then in year 2, I took the volatiles from the beer and basically created a blend, as beer is very diluted, 90 to 95% water. So this blend was a concentrated version of beer and was even more effective and cheaper than beer itself. And then the third year was comparing this organic based blend, which was derived from beer, to the leading pesticide in the industry. And what I found is that my agent, based on the beer, was equally as effective, while 4,700 times cheaper. But the issue was that after speaking to multiple beekeepers, we found that this treatment used in that plastic trap is extremely time intensive for use, and you have to manually count each of the beetles. So to account for this, I created a 3D printed IoT trap, which had IoT sensors and could automatically count the number of beetles that was showing up inside of the trap. So this is a fully automated system, and it was also using machine learning to take the inputs from that trap and predict future infestation levels in the hives to basically allow the beekeeper to see how the pest population is going to grow over time. And so the beekeeper can then personalize their pest management to that specific hive. So the materials and methods can be broken down into 4 key steps. The first was creating this 3D printed trap. The second stage was testing that trap for its accuracy to see what was showing up inside the trap versus what was being recorded by the sensors. And then the third step was creating that machine learning model to predict the future pest levels inside the hive. And the fourth step was evaluating the accuracy of that model over time. So this is what this trap actually looks like. And you can see on the left the trap. So this base that you can see holds the blend, which is the solution that's attracting the beetles. And when this is placed inside the hive, that blend that's inside the traps uses its smell, the odor of it, which attracts the beetles into the trap. And they then drown in this solution. So this has 2 sensors at the very top on each side, and the beetles enter to these slits and then drown in the solution. You can see in the middle, this is the wiring with the breadboards and the Raspberry Pi, which are sort of the brains of this interface. And then on the right, you can see the solar pack and the Wi-Fi router, which was used to transmit the data from this system to somebody's phone where they can see all of the data. So a beekeeper can go into a beehive and then see what data is being collected for that trap when they connect over Wi-Fi to the system. And this whole system was 3D printed. The LEDs were wired to this Raspberry Pi, the green device you see, through the breadboards. And this whole system costs about $13 per hive. So it's extremely inexpensive for beekeepers to use over the long run. And it costs half a penny per treatment cycle, so it's very inexpensive over time. The second stage was testing this trap inside actual beehives and then also in the lab. And basically, what was going on is seeing what was showing up inside the actual trap versus what was being recorded by the sensors to see what the accuracy of this system was like. And this was done both in the lab and in the field, where the trap showed accuracies upwards of 99%. The third stage was the development of the machine learning model, and this is created using 4,000 data points from previous years' worth of research. And the training size for the model was 70%, so it was learning based on 70% of the data. And then we would see how correct the model was based on the other 30%, which was the testing data. And the inputs for this model were the hive's strength from 1 to 5. So the beekeeper would grade the hive from 1 being the weakest and 5 being the strongest. And then the initial trap capture count, which is the number of small hive beetles, the pests, showing up inside the trap originally. And then using these two input factors, it could predict the future infestation levels for the hive. So a beekeeper will be able to see how the population is growing and then take personalized pest management measures to treat for the hive. So these are some of the results for this study. And you can see on the left, this is the trap that has been tested in the lab. And then on the right, you can see the trap that's been tested in the field. And the blue represents the true number of small hive beetles in the trap versus the red is the sensor recorded number. And there's no differences between these bars as you look across. So this means that the trap was very accurate. And for figure 15, this is the small hive beetle capture for the raw numbers in the blend with the 3D printed trap, which is in blue, and then the peach orange color is for the commercial trap. So we can see the blend is doing well in both the commercial trap and the 3D printed trap. And so these were all good signs that the blend was performing very well and the trap was also very accurate. And then these are the metrics for the residual plots. So basically seeing how that AI model is performing over time with its algorithm. And we can see that there's no residuals on the left plot. So the error was randomly distributed. And then for figure 17, there's no skewness and it follows a straight line. And we can see the error is decreasing over time in figure 18 and 19, which means the model is improving in its accuracy as we're feeding it more data. For the statistical analyses, the data showed that the lab and the field sensors were both accurate compared to the actual experimental counts. And this was done using a paired t-test. And the very large p-values showed that there was no significant difference between what was showing up inside the trap versus the actual counts for the sensors. So these were, again, all good signs. And moving to the discussion, the Comaphos that I compared in that third year of research has been the only EPA-approved pesticide that's used in the industry, but it's shown a lot of negative drawbacks. As you can see on the right, it causes the death of midgut epithelial tissue, and so it also disturbs the olfactory learning and memory formation in honeybees, overall reducing these pollinators' ability to forage and also just make a good impact in terms of what they're supposed to be doing. And so it also induces the downregulation of these two antioxidant genes in the honeybee gut, and it's basically just disrupting their immune system. So the blend that was created is composed of 4 volatile compounds that are all commonly used in food and beverage manufacturing. One of them is used as banana flavoring and baking. And unlike the previously used plastic traps that beekeepers were using, this trap on the right is reusable and has no negative environmental consequences. So it's reusable and it's also eco-friendly. And so overall, BeetleGuard AI is half a penny per hive, whereas Comaphos is $22 to $26 per hive. So there's an extremely big cost difference there, and it can save the industry 5.2 billion annually. It's 4,700 times cheaper. And apart from that, it's low cost, easy to use, eco-friendly, and personalized to each hive scenario. So after speaking to a lot of beekeepers and farmers, this is currently being integrated into an iOS app for beekeepers to use across the globe. And so it holds a lot of potential to boost agricultural productivity across the world. And so now we can move into our expanded dialogue with our implementation lab. So we can kick it off with segment one, and this is going to focus on climate smart pollinator protection. So Akash, let's start with you. So from your work on Varroa and carbon dioxide research, what does climate smart apiary management actually look like in practice? What sorts of tools are you using? And what sorts of pesticides currently exist on the market that your solution corrects?
Yeah, so currently the beekeepers globally, they're using integrated pest management systems called IPM. And what this really is these are pesticides that they use to intervene with all of these pests that are inside of the honeybee colonies. They do this to get rid of these pests. So they also have some non-chemical tools, and I'm developing the CO2 tool, as I mentioned. They also have organic treatments such as oxalic acid and other forms of acids that can be used to treat for these varroa mites. But there's a problem with these pesticide treatments that are currently used because these pesticides, as I mentioned, cause a variety of contamination inside of the hive, and they also lead to varroa mite resistance while having massive environmental implications because they contaminate the honey and bee products that we consumers consume on a daily basis, and they also contaminate the environment, which causes massive repercussions.
Yeah, so for segment two, from bee health to human health, um, basically zooming out and looking at how pollinator decline shows up in public health spaces, bees are an extremely big indicator of how an ecosystem is doing. And this has been mentioned by the Secretary General and climate experts as well. So bees are really seen as a keystone species. And as I mentioned earlier, a lot of farmers and beekeepers have this as their livelihood. So it's also taking a toll on the mental health of these populations and also indigenous populations. As we're seeing pollinators decrease, we're seeing a lack of and a plentiful resources in terms of their food stores. And these foods are just becoming less diverse and less nutritious as these pollinators are being harmed. And so overall, we're seeing hunger, and this is just negative in terms of the One Health lenses. The environment, animals, and humans are all interconnected. And if bees start to decline, then this affects other populations as well in terms of the food web. They perform 80% of pollination, and especially with a lot of these flowering plants and crops. If these crops cease to exist and these plants, then this affects herbivores, which affects carnivores, and this has impacts on and on up the food chain, which ultimately leads back to humans.
So we've heard a lot of, this week about data, transparency, and early warning systems, from city resilience dashboards to climate risk tools for finance. So what does an early warning system for bees actually look like on the ground?
Yeah, so at its very most basic level, it has to do a lot with basic sensors that are used inside the hive. And stuff that I was using in my research, it was extremely simple in terms of how it was working with the sensors. But it could detect these numbers and then just send, even on low bandwidth, such as 2G, signals to beekeepers and farmers to come out and actually check what's going on inside their hive. And this is pivotal, especially with a lot of the work that I was doing with farmers. Time is really of the essence in this process, and with these pests and a lot of pesticides that are being used, time is of the essence. The pest that I was working with has been shown to reproduce extremely quickly and can kill a hive in a mere week. So these early warning systems that use technology such as IoT and 2G are really able to help farmers and beekeepers in terms of managing their pest populations and keeping them at a low. And I think youth are really the key here, as they're growing up in this generation filled with technology, and they're working on all these interesting projects and are armed with all these tools. They really have the potential to use this technology for good in these agricultural environments. And so, moving on to segment four, which is finance and policy for scale, one of the biggest tensions at COP is in regards to finance and who will be paying for adaptation and how we can make sure that funds are actually reaching indigenous communities, such as farmers and beekeepers in places like the Amazon. So if you could change one policy and one financial mechanism, what would you choose to effectively scale pollinator practices?
Yeah, so on the policy side, I'd really push to fast track the regulatory pathways for low risk and eco friendly treatments that can be intertwined and used inside of the beekeeping industry. And this would give innovators, including youth innovators, a predictable way and roadmap to start developing and innovating. I'd also love to see innovation funds and mini grants awarded to start funding pilot programs so that people, different groups, youth, researchers, all of them can start to develop their own innovative treatments, peer review some other treatments that are existing, and work together towards finding sustainable and alternative treatments for these pesticides.
So yeah, that concludes this session. Thank you so much for listening, and we can open it up to any questions if you have any. But thank you so much.
Yes, sir.
Hello, I'm David Tavares from University of Federal Para, and thank you. Congrats for your presentation. And what's your the data set you use in machine learning, and what the model?
Yeah, so in our research, we were using a linear regression model. So I could basically go back and explain that a little further. But the model that we were using had these two inputs. And so this was the hive strength, which was a number, and then the initial trap capture count, which was also a number that was used. And we were plugging both of these values in and then seeing what the relationship was between them and the output that we were looking at. And then after doing this for those 4,000 data points that I was talking about, sort of like how linear regression works is that you look at the relationships between each of these variables and the output, and then you're able to create a line that has a bunch of the relationships captured between these factors. So you can basically see, given this data set, what does the average relationship look like for the data? And then given new data points, you can map this relationship and then see what the output will look like. And something interesting that could be looked into is something called continual learning. So this is where we're able to add new data that we're collecting over time and then retrain these models so we can personalize it to a hive scenario. For instance, if one hive is in a very warm temperature and this is affecting things in an adverse way, it wouldn't be that useful to train the model on a data set that was used for something that's located closer to the north, something that's colder. So with something like continual learning, we're able to continually train the model on new data and personalize it to each hive scenario.
Thank you very much.